All right, guys, so I'm going to take a couple of minutes to go through each of the questions on the binomial and Poisson practice from class. You're welcome to look through the ones that you want, fast forward, skip up to whatever questions you want. Hopefully you'll find this valuable. All right, so the first question we did in class: at a manufacturing plant, 35% of the employees work night shift. If 7 employees were selected at random, find the probability of that. Now, you should be able to look at this and recognize what type of distribution it is. You should recognize that if I take one employee, there's a 35% probability that one employee works night shift. Okay. Now this is asking about 7 employees, so it says take one employee, does it work night shift? Take the next one, does it work night shift? Take the next one. So each one of those employees is a different trial, and each one of those is the same probability that they work night shift. Okay. So what we're going to do is we're going to go into our calculator. We're going to go into Binomial Pdf, all right, to the binomial functions. So the first one asks about exactly 3 of those 7 working night shift. So we're going to go into menu, then we go down to probability. Now inside probability, we'll go down to distributions. Now once you're in distributions, you need to find binomial. You can either scroll down or scroll up. You see binomial. There's Binomial Pdf, Binomial Cdf. Right now, we're going to do Binomial Pdf, so I'm going to push enter. Pdf because we want one probability. Now, what we recognize is that first we have the number of trials. The number of trials is 7 because there are 7 people that are going to be looked at, 7 employees. The probability of success, or the probability of working night shift, because the question is asking about working night shifts, so the probability of that is 0.35. And then the x value is how many successes I want. Well, I want 3. Success here is defined as the night shift, so I want 3 successes. And so when I push enter, it gives me the probability right here, 0.267. So I'm going to write 0.268. And if I were doing this on an exam, I would make sure to write down this Binomial Pdf thing because it shows that I understand it's a binomial distribution and that there are 7 trials. Okay? Now, that having been done, we'll go on to the next part, which is at a manufacturing plant. We now have the question, less than 4 of them work night shift. So again, we're going to go into that binomial distribution. So we'll go into binomial distribution. And this time I'm going to do Binomial Cdf. The reason why I'm doing Cdf is because I want to accumulate several answers. Now, you could do PDF, right? Less than 4 means either 0, 1, 2, or 3 people work night shift. So if that's the case, you could just add those together. But if you do CDF here, then it'll allow you to choose the number of trials. Again, I'm looking at 7 individual employees. Each one has a 0.35 probability of working night shift. I want to go from 0 employees up to 3. And so that would be less than 4, and it gives me the probability of 0.800, just like that. Now, part C is that at least 4 of them work night shift. Now, I could go through, do the same thing, or I could recognize that that is the opposite of the previous one. So if 0.800, if that's the probability that less than 4 of them work night shift, then 4 or more should then be 0.200. And so that's question number 1, binomial probability. Let's go on to the next one. The next one says, road safety figures for a large city show that any driver has a 0.02% chance of being killed each time he or she drives a car. Now, I apologize. In class, I made this a little bit more complex than it needed to be. So I'm going to go ahead and walk through it again right now, and hopefully it'll make a little more sense. So this says, use Poisson approximation of binomial distribution to find the probability that a driver can use a car 10 times a week for a year and survive. So we're going to look at one driver here. So that means we're only going to have one trial that we're looking at. What's the probability that that driver survives for a year? Okay, so we're going to keep this 0.02, all right? We're going to say, okay, going to drive a car 10 times a week for a year. So that would be 10 times 52 weeks. So that would be 520 times they're going to drive the car. Now remember, for binomial, the expected value, which is the mean, is simply NP, right? The number of occurrences times the probability of that occurrence happening, which is basically what I just did. I took I'm going to take the number, which is 520 times. So 520 times they're going to drive the car, and the probability for each one is 0.0002 because it's 0.02% chance, so move it over twice. And so then we get a probability of 0.104. Okay, so that is the expected value that you will not survive. Now, that being given, we're now going to use a Poisson distribution to find the probability of surviving. Okay, so the Poisson distribution, we can just use Poisson Pdf. You can also use the equation, do it by hand if you want, but I'm going to use this right now. So we'll go into distributions. Note that just like there's a normal CDF, there's also, and binomial CDF, there's also a Poisson PDF and CDF. So I'm going to do Poisson PDF, okay, because this right here is the probability of a death, right, of being killed out of those 520 times. Now, the PDF I'm going to do because I'm going to put 0.104 in for that. And then my X value, well, I want 0 deaths, right? If I survive, that means I have 0 deaths. So I'm going to put in 0, and then it's going to solve, and it's going to give me my probability right there, which is probability of survival or deaths equal to 0. That would be 0.901. All right. Now, part B says, if this data does not change, how many years can you drive and still have a better than even chance of surviving? So in order to do this, we're going to have to be a little bit more creative, but basically we just need to find out how many times we need to be able to do this before we get to 0.5, right, a 50% probability. So the first year, I have a 0.901 chance of surviving. If I survive the next year, then that would mean that I survived the first year and the second year, which would be 0.901 again. If I survive the next year, that means that it would be 0.901 again, right? Each year that I survive, I multiply by 0.901 again. Or in other words, it's going to be 0.901 to the power of the number of years. And of course, we want this to be greater than 0.5. I want to have a better than even chance of surviving. So we should now be able to solve this, right? Take log of both sides. So log of 0.901 to the n power is greater than log of 0.5. Move the n in front, that's one of our log rules, and then divide by log of 0.901. So n is going to have some relationship. Now, we're not quite sure what logs do to the inequality, so leave it for now. So n is somehow related to, I'll put equal sign for now, log 0.901 over log of 0.5. Man, this is what you get when you don't sleep. These should be switched because the n was here. I'm actually going to divide by log of 0.901. So I need to flip those. So this will be 1 divided by the answer. So there we go. So 6.64 years you expect to last. So therefore, 6 years, you can drive for I think you're probably okay writing this. So 6.65 years average survival. Okay, so there you go. So hopefully that made sense. Remember to find for a year. We found out how many times they were going to drive in a year, multiplied by the probability of surviving each time, and then we got a probability for that year. Once we had the probability for the year, we looked at a specific individual And by look, because remember, this is just an average, right? This is the expected value. So then we need to look at the average, because some people would die in that time. Some people could die twice if they actually got to 520. Obviously, that doesn't make sense, but the probability says it could happen. So therefore, we use the Poisson distribution to find out what is the probability of death being 0. That gave us our probability of survival, which was 0.91. We used, remember, the Poisson Pdf for this. Okay. Then we went and we figured out how many times this could happen, how many years in a row, until it dropped below a 50% chance of surviving, which was 6.65 years. Okay, anything past that, and you have a less than even chance of surviving. All right, very good. Let us move along. So, a city restaurant knows that 13% of reservations are not honored, which means the group does not come. Suppose the restaurant receives 5 reservations and X is the random variable on number of groups that do not come. Find the mean and the standard deviation of the X distribution. So for this one, X is the number that do not come. And then 0.13 is the probability that they do not come. Okay, so the restaurant receives 5 reservations. Okay, what kind of distribution is this? Well, hopefully you recognize that this is a binomial distribution, right? Because each reservation is a new trial, and so we say this is binomial. They each have the same probability, 0.13, and we're going to repeat 5 times. So here it says find the mean and the standard deviation. Well, the mean, remember, if you think about your formula packet, the mean for a binomial distribution is simply NP. Okay, so we're going to do that. So we're going to say expected value, which is equal to the mean, is NP, which is just going to be 5 trials times 0.13. So therefore, the expected value is 0.65. So maybe half of the time, one of those 5 will a little more than half the time, one of those 5 will not show up. Okay, the second question asks for standard deviation. Again, we go back to our formula packet. Remember, in our formula packet, we again have binomial distribution. It doesn't give us standard deviation, but it does give us variance. It says that the variance is equal to NP 1 minus P. So, therefore, variance, which is sigma squared, equals NP times 1 minus P. So that would be 5 times 0.13 times 0.87, 1 minus that probability. So we go ahead and put that into our calculator here. 5 times 0.13 times 0.87, and we get 0.5. It doesn't show up very well on the screen there, but it is 0.5655. So therefore, variance, which is our sigma squared, is equal to 0.5655. So to get standard deviation, we're just going to square root that answer. So standard deviation is 0.752. That's my final answer, so I'm going to leave 3 significant figures there. All right, so that was a little bit easier one. Let's move on. So this one will be another one. It obviously tells us that it's Poisson. It says that it has a mean of m and satisfies this. So the probability of y being 3 is equal to the probability of y being 1 plus 2 times the probability of y being 2. Okay, so 3 is obviously more likely than 1 and 2, even more than 1 and 2 combined. This says find the value of m correct to 4 decimal places. Well, I don't know what to do here other than the fact that they gave me the probability of some y's, and so I'm going to see if I've got a formula for that. And yep, there we go, right there. See, this formula right here says that if x is a Poisson distribution, then the probability of x is equal to m to the x e to the negative m x factorial. So I'm going to put that right up here at the top so that we can see it. I'm going to copy it down. So the probability of x is equal to m to the x e to the negative m all over x factorial. Okay? And so let's then see if we can use this. So I'm going to use the probability that y is 3. So that would be m to the third e to the negative m all over 3 factorial. So I put in 3. That's my x equals 3, y equals 3. That needs to be equal to the probability that y is 1. So m to the first power e to the negative 1 all over 1 factorial plus 2 times y being 2. So m squared e to the negative m all over 2 factorial. So basically, I've just rewritten the formula 3 times for the probability of 1, 2, and 3. From here, there's only one variable left. I should be able to solve. Okay? So I'm going to go ahead and pause this. Why don't you try to work through it? I'll go ahead and put my work here so that you can check it, but I'm going to try to keep this video a little bit shorter. Ta-da! Is that what you got? Well, hopefully you just went and you simplified. I simplified the factorials, multiplied everything by the greatest common denominator 6 to get rid of denominators because I don't really like dealing with fractions if I don't have to. I also at the same time divided by e to the negative m because they all had e to the negative m. And so that got me to this cubic right here, moved everything over to the other side, and then I factored out the m. At this point I recognize that m is my mean, it's also my variance. So unless the variance is 0, then it probably is not important for it to be there. So the variance is not 0, so therefore that's not really a solution. So then I went and I solved this using the quadratic formula. I got a plus and minus. Again, because x is m, that's the x that I put in here, because that's m being the variance can't be a negative number, therefore it was the positive solution, which was 6.87. So 6.87 is my average, my mu. Okay, that is the mu. It's also the variance. At this point, I can go on to part B. Using the value of m found in A above, find the probability that y is between 1 and 5. So of course for this, I'm going to pull out my calculator. Okay, so I'm going to pull out the calculator and we're going to go menu, probability, distributions, and I'm going to go up to Poisson Cdf. Okay, that's my mu, so 6.87. I want a lower bound of 1 and an upper bound of 5. Now I want to make sure that y is between 1 and 5. Now remember, Poisson is a discrete situation. It's not continuous. Because Poisson is discrete, then I need to make sure that I don't include 1 or 5. And so I'm going to go ahead and change this to a 2. If you don't like that, then you can say, well, make this 1.0001. It's the same thing. It doesn't matter. And then you could make this 4.9999 to make sure that you don't include the 5. But like I say, it's not going to matter. So I'm just going to go from 2 to 4. And then we say OK. And it gives us the probability that we are looking for. And so that is the answer to part B. So 0.177. Part B. Again, if I were doing this on exam, I would write down that I did Poisson Cdf, that I used 6.87 for the mean, and I went from 2 to 4. Okay, that way I can at least show that I knew I was supposed to use Poisson Cdf. And then the last question is calculate the probability of y being between 2 and 6 inclusive, given that y is less than or equal to 4. So therefore, greater than or equal to 4. So that means I'm going to use my given formula. Right, the probability of A given B is equal to the probability of A and B, both being true at the same time, divided by the probability of B. Please use the given. So now I need to find the probability of B, which is y is greater than or equal to 4. So I'm going to use my calculator for that. So I'm going to go probability, distributions, Poisson, Cdf. So I'm going to say 6.87. My lower bound is going to be 4 or greater. So to go greater, I'm going to go 9E, 9 or 99. It doesn't really matter. I'm going to say OK. Sorry, it doesn't like my 9099, so let's go ahead and try that again. It doesn't like those big numbers, does it? There we go. Going up to 100 is fine. So the probability of B is 0.911201. So that's the probability of it being greater than 4. Okay, and then I need the probability that it is both between 2 and 6 and greater than 4. So therefore, the only thing that's both between 2 and 6 and greater than 4 would be anything between 4 and 6, right? Because if you think of this kind of as a Venn diagram, right? You've got the values which are between 2 and 6, from 2 to 6, are within this circle. Greater than 4, some of them are in here, right? Some of those greater than 4 are here. These values are greater than 4. They're also between 2 and 6. The rest of these are greater than 6, so they're not within that. And so the intersection is the and are the ones that are between 4 and 6. So again, I'm going to come back to my calculator, and I'm going to do Poisson Cdf, but I'm only going to get the ones between 4 and 6, which is going to be 0.380. And so now I'm going to take those two numbers. So I'm going to take the answer, and I'm going to divide by 0.911201, and I push enter, and I get the answer of 0.418. And that is the final answer to this question. All right, hopefully that is good to go. Let us move on to the last question. Okay. This is the one that we did at the very end of class. Just want to make sure that I talked through it again, just in case, to make sure that everybody's all right with it. So this one is: a carpet is manufactured. Small faults occur at random. The number of faults in premium carpets can be modeled by a Poisson distribution with mean 0.5 faults per 20 meters squared. Mr. Jones chooses premium carpets to replace the carpets in his office building. The office building has 10 rooms, each with the area of 80 meters squared. Okay, so the first thing we need to do is find out the probability of faults in an 80 meter squared carpet. Well, it's 0.5 faults per 20 meters. So within 80 meters, then I will get 2 faults, right? 0.05 times 4, because 20 times 4 is 80. Okay, so I've got 2 faults for each 80 meter, okay, on average. So now what I want to do is I want to look at what is the probability that the carpet in the first room, so looking at one carpet, what is the probability that it has fewer than 3 faults? Okay, now this says that it is a Poisson distribution, so I'm going to use the Poisson distribution, and I'm going to go for fewer than 3 faults. So here we go. We're going to go Poisson Cdf, so probability, distributions, and then Poisson Cdf right there. That's your M, your mean, which is 2 faults. And then I want less than 3 faults, so from 0 to 2 faults. And I get 0.676676. Okay, now I'm going to write this down for my answer, because my answer is going to have 3 sig figs. But I'm also going to remember these digits, because if I do further calculations, I'm going to go ahead and use all of the digits. Okay. Part B says find the probability that exactly 7 rooms will have fewer than 3 faults. Now this one was only looking at one carpet. That's why I looked at the Poisson, was the probability of that one specific guy, that one specific carpet. But now I'm looking at 7 rooms with fewer than 3 faults, exactly 7 rooms, but that's out of the 10 rooms that we started with. Okay, this should sound a lot like a binomial distribution. 10 different rooms, each one with exactly the same probabilities of faults. Okay, so this is now a binomial distribution. And that's the hardest part of this question, is recognizing that the first question is Poisson, the second question is binomial. So I'm going to go into my binomial distribution. Okay. binomial this time, and it's asking exactly 7 rooms. So that's a Poisson, a binomial Pdf. The number of trials, so I'm in binomial Pdf. The number of trials is 10 rooms. The probability of having fewer than 3 faults is 0.67, and then remember it was 6676. Okay, and then the x value is how many I want to have fewer than 3 faults, which is 7 rooms. And we go OK, and it gives me my final answer, which is 0.263. And that is our final answer. All right, so there you go. Work through each of the questions in that worksheet. Hopefully that's helpful. Use this as you review tonight, and hopefully that will help you be prepared for your upcoming celebration.